Hi students, today we're going to be going through some of the practice problems from the notes on limiting and excess reactants in your course pack. So you should grab that out. It should look like this, and the beginning of it of course actually has some questions and a place for you to write some notes about, like how do we determine which one the limiting and excess reactant were. And so if you weren't able to get that down from other videos, maybe as we go through some of these practice problems together, you can come up with a list of, this is how we approach these problems. Now before we even start, the whole idea of a limiting reactant is that anytime we have more than one set amount of a reactant, one of the reactants we're using is going to run out. That's just the whole concept here. And so in this first problem, we have 100 grams of C2H6 and 200 liters of oxygen gas at STP. And we need to figure out when this reaction runs, which one's going to run out first. Whichever one runs out first also produces the least amount of reactant. The least amount of product. And so that particular reactant is going to be our limiting reactant. So how do we start this? Now, first, if you don't understand how to do stoichiometry yet, you need to get that down. So if you're having trouble using mole ratios to convert between substances in a chemical reaction, I'd highly recommend you first go and do some practice and check some answer keys on that, and then you'll be able to understand what we're doing a little bit better here. So let's go ahead and get started. On my new page here, I'm going to transfer over my 100 grams of C2H6 and then my 200 liters of oxygen gas at STP. Now, before we can do anything with this, we need to go ahead and write the balanced reaction. So we'll go ahead and write that down here. Now these are your two reactants for this reaction, and based on our last unit, you should be able to predict the products here. So take a second and predict the products. If you came up with CO2 and H2O, then you're right. Now take a second, pause the video, and balance the reaction on your own paper. For your coefficients, you should come up with 2, 7, 4, and 6. Now that we have our balanced reaction, we can go ahead and start figuring out which one the limiting reactant is here. Now, again, we have 100 grams of this substance, the ethane, and we have 200 liters at STP of the oxygen gas. What I'm going to do now is just do stoichiometry. I'm going to pick one of the two reactants. One of the two products, and I'm going to take both of my amounts of reactant to that particular product to figure out which one makes the least amount of product. There are other ways you can solve this problem, but I'm going to stick with this where we take each of the reactants to one of the products. And so in this case, I'm just going to randomly pick carbon dioxide. It's not quite random, I guess. Over here at the bottom on number 4, it asks what's the theoretical volume of CO2 gas in liters. And so I'm going to go ahead and solve this for liters of carbon dioxide, and then I'll also be answering number 4 as well. So we're going to start with my 100 grams of ethane here, and we're going to do stoichiometry to go from 100 grams of this to liters of CO2. Pause the video and take a second to see if you can write the 3-step conversion to go from 100 grams of ethane to liters of carbon dioxide gas at STP. Alright, so we have it set up. This is what it should look like. The first thing we want to do is go from grams to moles of ethane. And so I know 1 mole of the C2H6 has a molar mass of 30.08 grams. Notice that my grams up top and my grams on the bottom here so that they'll cancel. So I'm going from grams to moles of the ethane here. The next step, we're going to go ahead and use our mole ratio to go from moles of ethane to moles of carbon dioxide. So we can see from the balanced reaction that 2 moles of the ethane will yield 4 moles of CO2. So that's my step in the stoichiometry where I'm converting from my reactant here, okay, to my product here. Now the last step, one thing to note, we can stop now and just calculate for moles of CO2, and then we could go to our oxygen and find out how many moles of CO2 is produced from the oxygen. So it's perfectly acceptable to stop at moles and solve right here. Sometimes that confuses people, and since we know we're going to have to go to liters at STP of carbon dioxide based on question number 4, we'll just go ahead and go all the way to liters of carbon dioxide gas. So we know 1 mole of carbon dioxide gas will have a volume of 22.4 liters, as long as it's at STP, and in the problem it tells us it's at STP, or that's what it's asking for. And so we'll go ahead and assume that here. And when we solve for that, it's about 149. And if we look at sig figs here, we were given 100.0, so that's 4 sig figs, so 149.0 liters of CO2. Okay? All right. Now, that doesn't tell us the whole picture, because we also have to figure out now how much CO2 the oxygen gas would produce. And so take a second and determine from 200 liters of oxygen gas at STP, how many liters of CO2 at STP will we produce? So let's go ahead and set it up, if you didn't do so already. And our first step here is going to go to get our oxygen from liters to moles. And so we know that there's 22.4 liters of oxygen gas in 1 mole of oxygen gas. Okay. Now we're going to use our mole ratio, just like we did up here. But this mole ratio is different. We can see that 7 moles of O2 will yield 4 moles of CO2. Right. Again, if you stopped up here at the top part, if you stopped at moles here, this is where we want to stop, and that would be perfectly fine to determine which one makes the least amount of moles of CO2, and therefore being our limiting reactant. But again, I'm going to go ahead and take this all the way to liters at STP, just like we did in the problem above here. And so 1 mole of CO2 will have a volume of 22.4 liters at STP. Okay, now when we calculate that out, you'll notice that the volume produced from the 200 liters of oxygen gas is around 114.3 liters. And now when we go compare these, what we're looking for is which one makes the least amount of carbon dioxide, which one makes the least amount of product. Well, how does that tell us the limiting reactant? Because the one that makes the least amount of product is the one that's going to run out first. So if we look at this, this is the least amount of product, which means this is our limiting reactant. Now, one thing that tells us is this number right here that I just crossed out, that number is not valid for anything. There's no way that we can actually make that much carbon dioxide gas because we don't have enough oxygen to do that. For that reason, we're going to cross this number out and we're never going to use it again. It's not going to be a number for us to be able to use. So now we've determined, because this is the least amount of product, that oxygen gas, this right here, is our limiting reactant. Now, what does that mean about the 100 grams of C2H6? That means this is our excess reactant. Okay, so I'm going to abbreviate that ER for excess reactant. Now, if we go back to the question here, it says, number 4 here says what theoretical volume of CO2 gas would be produced in liters from the amounts given. Now, we already solved for that. we see here that we would produce 114.3 liters of CO2. So that's actually our answer for number 4. All right. We also figured out here which one the limiting reactant is. That's the oxygen gas. Okay. Now the next question is, how much of the excess reactant will be left over from question 2? We know that when we're done, there's going to be no oxygen gas left. It's going to all run out. But that means we're going to have some leftovers of the ethane. So there's going to be some of this left over, and we want to figure out how much that is. So how do we do that? Again, there's several different ways to do this, but one of the ways is to take our 200 liters of oxygen gas and determine how much of the ethane we would use, how many grams of ethane we would use with 200 liters of oxygen gas. So we'll go ahead and do that on the next page here. So I'm going to go ahead and set up my problem, and I'm going to figure out with my 200 liters of oxygen gas, which is my limiting reactant, how many grams of ethane would we produce. Now, why would I want to use grams? The reason I want to use grams is because we're given grams here. Okay, that means that I need to figure out from my 200 liters of oxygen gas, how many grams of CH2 of that 100 am I going to use? And then we're going to end up subtracting those numbers, like what we started with, from what we would use, and that'll give us what's left over. And so that's why we're going to go to grams. If this amount here had been in liters or maybe in moles for some reason, then that's what we would solve for. So whatever our excess reactant units are, that's what we want to solve for when we're going from the limiting reactant amount to the excess reactant amount. So let's set this up. 200 liters of oxygen gas, and we know that it's 22.4 liters of oxygen gas is 1 mole of oxygen gas. Okay, that gets us to moles. Now we're going to use the mole ratio going from oxygen to ethane. So that's a 7:2 ratio. Okay, so 7 moles of O2 will yield 2 moles of the ethane. Okay, now we'll be at moles of ethane, but we want to get to grams, as I mentioned. So we know 1 mole, every 1 mole of the ethane has a molar mass of 30.08 grams H6. And when we calculate that out, we see from the 200 liters of oxygen gas, we actually produce, or we would consume about 76.71 grams of the C2H6. So what do we just figure out? We figured out when we use 200 liters of oxygen gas and it's all used up, we will have used 76 grams of the excess reactant. Now remember, how much do we start with? This is a common mistake. Don't stop here, because it's asking for how much is left over, not how much you actually used. How do we determine leftovers? We take what we started with, okay, and we subtract it from what we used, all right? And that's how much is left over. So how much did we start with? 100 grams, right? Back here in our problem, we started with 100 grams of this. We used this amount with the oxygen, 76.71 grams. And again, I'm paying attention to the sig figs. I don't know if you've noticed, but I guess I didn't put my decimal place in here. It's 200.0 liters. But pay attention to those sig figs as you're going and use those skills that we've taught you. When you subtract this up, you get 23.3 grams of the ethane that's left over. Okay, so in this reaction, we used about 76 grams of it. We started with 100 grams of it, and so we had about 23 grams of that reactant left over. So that answers this question, number 3 here, of how much of the excess reactant would be left over. Okay, let's go ahead and check out the next problem here. Your numbering may be different on mine. It's number 17, but it doesn't matter the problem. If you read the problem here, you'll see what we're working with. So we're looking at the reaction here between sodium phosphate and barium nitrate, and that reaction yields barium phosphate and sodium nitrate. You should recognize this type of reaction. This is a double replacement reaction, and we also can tell that this reaction actually takes place because remember we start with 2 aqueous compounds here, and when we mix them together we get a solid precipitate. So that's a good indicator of what's going on. So anyway, we have 3.5 grams of the sodium phosphate here, and we have 6.4 grams of the barium nitrate here. And we need to figure out first how many grams of barium phosphate can theoretically be formed. Now, this is a limiting reactant problem. The way we know it's a limiting reactant problem is because we have amounts of more than one of the reactants. Sometimes in a problem you'll see, for example, maybe 3.5 grams of sodium phosphate reacts with excess barium nitrate. And that just means that it's not a limiting reactant problem because, I mean, we already know the limiting reactant because we're limited on how much of this we have. But in this case, we have amounts of both reactants, and so we have to figure out which one is going to limit us to the least amount of product. And this is specifically asking us about how much barium phosphate will be formed. So that's what we need to solve for in our problem here. So let's set this up. I went ahead and created some units here for my purposes because trying to write these in takes a long time and it's very difficult. And so here we have the balanced reaction. We can see that there are 2 moles of sodium phosphate will combine with 3 moles of barium nitrate and yield 1 mole of barium phosphate and 6 moles of sodium nitrate. And so we're going to go ahead and start with the amount of each of these. And if we go back real quick, we have 3.5 grams of sodium phosphate. So we have 3.50 grams of this. And we have 6.40 grams of this. And we need to figure out how much barium phosphate in grams is going to be produced. So back to like our last problem, what we want to go ahead and do is take our amount of one reactant and go all the way to the product here and take the amount of the second reactant and go to product. But we're going to do this in 2 steps. So we'll start with the first one here. So the first problem we're going to set up, I'd like you to go ahead and pause the video if you haven't done this already. Go ahead and take the 3.5 grams of sodium phosphate and determine how many grams of barium phosphate will be produced in that reaction. Alright, so we'll go ahead and set this up. I'm going to put my units in a minute since my wonderful smart program is not very smart. So we're going to go from grams of the sodium phosphate to moles. 163.94 grams of the sodium phosphate is 1 mole of the sodium phosphate. Okay, so now we're going to go ahead and go to our next step, and we're going to use the mole ratio to get to the barium phosphate up here. So I know from my balanced equation up here that 2 moles of the sodium phosphate will yield 1 mole of the barium phosphate. And then we'll go ahead and finish this off going from moles to grams. So 1 mole of the barium phosphate has a molar mass of 601.92. Alright, I'm going to pause and put my units in here. Alright, this is what it looks like with the units. So I'm just going to cross these off. Grams of sodium phosphate cancels. Moles of sodium phosphate cancels. We go to moles of barium phosphate and that cancels. And we're left with grams, which I didn't write in there, of barium phosphate. When we calculate that out, it's about 6.43 grams of the barium phosphate that would be produced from this much of the sodium phosphate. Now we have to do the same thing with the amount we're given here of the barium nitrate. So we're going to take the 6.40 grams of barium nitrate and do the exact same thing and go to grams of barium phosphate and see which one of these produces the least amount. So again, pause the video, find these molar masses, calculate those, and do the stoichiometry, going from 6.40 grams of the barium nitrate all the way to grams of the barium phosphate. Okay, so we're going to go ahead and use the molar mass of the barium nitrate, which is 261.37 grams per 1 mole of the barium nitrate. Okay, and then we're going to go ahead and use the mole ratio, which we can see is a 3-to-1 ratio. 3 moles of the barium nitrate will produce or yield 1 mole of the barium phosphate. Okay, and then down here we'll go ahead and convert it to grams by doing 1 mole of the barium phosphate has a molar mass of 601.92 grams. Notice that this step here is the exact same as this step here, because we want to end with the same units on both of these so that we can compare them. So here's what it looks like with the units. Okay, we can see we went from grams to moles, and then moles of barium nitrate to moles of barium phosphate. And the key thing is here we're going to end with grams of the barium phosphate for both of these. So when you calculate this out, you get 4.91 grams. Now, which one is the limiting reactant? Remember, we're not asking about there's no limiting product. We're asking about over here between the 3.5 grams of sodium phosphate and 6.4 grams of barium nitrate. Which one of these two is our limiting reactant? So again, which one made the least amount of product? Here, let's do this. So my limiting reactant is the one that made the least amount, and this is the least amount, and so I know my limiting reactant is the barium nitrate here. So this is my limiting reactant, which means that the sodium phosphate is my excess reactant. That means when I use up all 6.4 grams of the barium nitrate, I'm going to use some of this 3.5 grams of sodium phosphate, but not all of it, and we're going to now figure out what that is. So going back to the question here, it asks us how many grams of the barium phosphate would be produced, and that's what we just figured out. It would be this 4.91 grams right here. Okay. Now again, the next question was what is the excess reactant and how many grams are left over of the excess reactant? For this problem, we need to do just what we did in the last one. We need to go from our limiting reactant. All right, let me go ahead and just stay with my pen colors here. And we're going to go from the limiting reactant to the excess reactant, meaning I'm going to figure out from the 6.40 grams of the barium nitrate, how many grams of the sodium phosphate will I use up when I use all 6.4 grams of the barium nitrate. All right, so let's go and set this up. We're going to start with our 6.40 grams of our limiting reactant. Okay. All right, so start with this. I'm going to use the molar mass here to go to moles, so grams of barium nitrate to moles of barium nitrate. Now I need to get the mole ratio, so go back to our reaction, and we see that it's a 3-to-2 ratio here. So 3 grams of the barium nitrate, 3 moles of the barium nitrate will consume 2 moles of the sodium phosphate. And now the last step is I want to get this to grams. And remember, why do I want to get it to grams? Because the problem, we're given grams of our excess reactant. And so in order to subtract those, we have to have the same units as what we were given in the problem here. So I want to get to grams of the sodium phosphate here. So moles, 1 mole of the sodium phosphate has a molar mass of 163.94. And I'm being bad with my units, I apologize, but trying to fit these on here is a bit ridiculous. And when we calculate this out, what we figure out is with the 6.4 grams of the barium nitrate, we use 2.68 grams of the sodium phosphate, which is the Na3PO4. Okay. Now, how much did we start with? We started with 3.5 grams. We only used 2.68 grams. So to find out how much is left over, let's take what we started with, how much we used, and how much is left over. We're going to subtract those. So we started with 3.50 grams. We would use 2.68 grams. And when we subtract these, right, we get about 0.82 grams of the excess reactant is in excess, or is left over, PO4. Okay, that's the answer to this question right here. Okay. Now, as I mentioned before, there are multiple ways to do limiting an excess reactant problem like we've just demonstrated. I want to show you one other way. Most students are perfectly comfortable using the method I just taught you, where we pick one of the products and we take each reactant to that product, and whichever one makes the least amount, that's our limiting reactant. But another way to do it is just to compare the different reactants and how much they actually might make between each other. And so here's how we would approach this. We're going to say, okay, if I had 3.50 grams of the sodium phosphate, okay, and then we would actually figure out, we would go from here to here and go, well, how many grams of the barium nitrate would be needed to react with the 3.50 grams of sodium phosphate? If we do this problem, well, let's go ahead and we'll work it out. And again, my units are going to be a little funky here. I apologize. So we're going to start with the 3.5 grams of the sodium phosphate. It doesn't matter. I could start with the 6.40 grams of the barium nitrate. I could use that as well to start with. It doesn't really matter, but you'll see the process here. So we're going to go ahead and go through 163.94 grams of the sodium phosphate is 1 mole. All right, and we'll use the mole ratio so 2 moles will produce 3 moles of the barium nitrate. All right, and the last step is to get that to grams. Again, you can stop at moles if you want, but we actually we need to get this to grams so we can compare the 6.40 here to how many grams we would use at the 3.50 grams. And so we know 1 mole of the barium nitrate has a molar mass of 261.37. So here's with the units in there, and when we calculate this, all right, we see that we get 8.37 grams of the barium nitrate that would be used. Now, how do we use this to determine the limiting reactant? What we just figured out is if we used all 3.5 grams of sodium phosphate, we would need at least 8.37 grams of the barium nitrate. We don't have that much barium nitrate. We only have 6.40. What that tells us is that we would run out of the barium nitrate before we ran out of the sodium phosphate, which means the barium nitrate is our limiting reactant. Now, had this number here, we calculated it, had that have been less, that would mean that the 3.5 grams of the sodium phosphate would need less than we actually had of this number. And that would mean that the sodium phosphate is the limiting reactant, but it's not. And so we can determine from this one problem that the barium nitrate is the limiting reactant problem, or is the limiting reactant in this problem. Now, this only answers part of the question because it only answers which one is the limiting reactant. We still would have to go now back here using the amount of the limiting reactant, the 6.40 grams from up here of the barium nitrate, and we would have to take that to grams of the product we're looking for, the Ba3 barium phosphate here. 2. Shoosh. Okay. So we already did this. We pretty much already did that in the last demonstration I showed you. And so we would know that it was 4.91 grams of the barium phosphate. That's what we calculated. But this is just a different way to solve the problem. It's still 2 steps. And so at some point, you have to decide which one of these processes works the best for you. And you're going to have to choose that. So where you should go from here now is you should go ahead and move on to the on your own and spend some time practicing the on your own. And then if you have any questions, you should contact your instructor and we can help you further.